History of the Atom Project, Part 2. We left off with Rutherford's model, but there were a few things that were wrong. Rutherford's model did not account for the properties of electrons, and atoms seemed to be too stable. They were expected to collapse when electrons absorbed or released energy. It also does not obey the conservation of energy, so let's rewind all the way back to 1900 with Max Planck. In 1900, a German physicist named Max Planck developed the quantum theory of energy and was awarded the Nobel Prize in 1918. He proposed that energy is radiated in discrete quanta-sized packets, rather than in a continuous wave. Planck called these packets quanta and was able to determine that the energy of each quantum is equal to the frequency of the radiation multiplied by a universal constant that he derived, now known as Planck's constant. To simplify, Planck's constant is used to describe the behavior of particles and waves at the atomic scale. Though at the time this was all just an assumption, and this brings us to our next scientist, Albert Einstein. Later in 1905, with Einstein's interpretations, Planck's calculations were proved. He also explained the equivalency of mass and energy expressed by the famous equation E equals mc squared through the question he asked himself. If a person was flying in space at the speed of light with his arm fully outstretched holding a facial mirror, what would they see in the mirror? Would they see their face? Would he be distorted in any way? Would light waves have time to bounce off their face, hit the mirror, and bounce back to their retina, which was also moving at the speed of light? He also mathematically proved the existence of atoms with the use of statistics and probability, through the use of a theory called Brownian motion that was later developed. Next is Niels Bohr. Niels Bohr used Rutherford's model and Planck's constant theories about quantum mechanics that described electron behavior to make a model that was accepted for the better part of the 20th century. In 1913, he proposed a theory for the hydrogen atom based on quantum theory that energy is transferred only in certain well-defined quantities. Electrons should move around the nucleus but only in prescribed orbits. When jumping from one orbit to another with lower energy, a light quantum is emitted. His atomic model looks like this. Next we have Heisenberg. One of his most memorable discoveries is the uncertainty principle. This means that electrons do not travel in neat orbits and that the exact knowledge of complementary pairs of position, energy, and time is impossible to figure. He also calculated the behavior of electrons and subatomic particles that make up an atom. He named the electron cloud, which is the name given to the electrons that are widely spread out and moving around the atomic nucleus. Brings us to our final scientist, Schrödinger. In 1926, Schrödinger combined the equations for the behavior of wavelength with the de Broglie equation to come up with a mathematical model for the distribution of electrons in an atom. This model consists of mathematical equations known as wave functions that satisfy the requirements placed on the behavior of electrons, and it describes the probability that an electron can be found in any given region of space at any time. This is what Erwin Schrödinger's atomic model for carbon looked like. Since 1932, through continued experimentation, many additional particles have been discovered in the atom. The theory of the composition of the atomic model is an ongoing process. Today, electrons are in constant motion around the nucleus, protons and neutrons wiggle within the nucleus, and quarks jiggle within the protons and neutrons. This is what the atomic model would look like today. Thanks for watching!